everyone for joining and welcome. Today we're going to hear from Karl Ove Ingebrigsten. I hope I said that right. I probably did not get your last name very well, Karl Ove. And Karl Ove went on a volunteer assignment to Gaziantep, Turkey, where he worked alongside two engineers who are here today as well, Zakaria Al-Samu and Al-Muthana Al-Sharif. And Karl Over's assignment, which we'll hear more about, was around risk assessment of the polyfloss machine. And Field Ready, or Sahaya Hazir, as they are known in Turkish, are our partners in the Waste for Warmth project. So what I wanted to first do is just share a very brief bit of information about Waste for Warmth. So if you all can see this slide, Waste for Warmth is a consortium project between Engineers Without Borders Norway, Field Ready or Sahaya Hazar. They're located, as I said before, in Gaziantep, Turkey. And then the polyfloss factory. And the polyfloss factory is the manufacturer of the polyfloss machine, which we'll learn a lot more about later on in this presentation. And so Waste for Warmth, the project itself uses waste plastic to turn in and make insulation products for warm and safe shelters and provide work opportunities for displaced people. So the last thing I'll just say about Waste for Warmth, and you're always encouraged to reach out to me if you want to learn more, is that the really exciting thing about the Waste for Warmth project, and one of the things that makes it really innovative, is that there's a lot of different benefits to the project, a lot of different objectives. We can remove waste plastic from the environment and create this circularity with plastic, which is really a resource. There's job opportunities created for displaced people. At the heart of it is we're really trying to increase the warmth in shelters during winter conditions, which we hope leads to a decrease in burning unclean heating fuels for warmth, which would also lead to a reduction in respiratory illnesses amongst people living in these shelters, and also a reduction in greenhouse gas emissions by manufacturing insulation locally. So the traditional humanitarian supply chain often sees goods being shipped around the world. And I guess I'll share one more slide. Gaziantep is located really close to the border with northwest Syria, where there's over 2 million displaced Syrians currently living. Last winter was particularly harsh. There was a pretty severe snowstorm that hit the region, as well as Gaziantep itself too. And temperatures fell to -5 degrees Celsius. And so there's just a really big need for insulation for people living in tents and transitional shelters. So I'm going to now turn it over to Zakaria and Al-Muthana, who are going to share a little bit more about Sahaya Hazir and the work that they've been doing before we hear from Karl Ove after them. So if you want to share your slides, Zakaria or Al-Muthana, please go ahead.
Okay, thank you very much, Holly, for the short introduction. And I'm going to, brief you with the Field Ready Turkey. First of all, I would like to share the presentation with you. Okay, so yeah. So hello, everyone. I would like to first of all to thank the organizers of this meeting, the Norwegian Engineers Without Borders, for inviting us here today. And it's an honor to have the opportunity to add such this distinguished, audience. Today, I would like to give you an overview of what the Field Ready does and its, previous projects and its current, activities that are being carried out in collaboration with the engineers without border NORI and the polyfloss factories. Field Ready is a group of engineers. Sorry. It's fine. Yeah. So Field Ready is a group of engineers, humanitarian, aid and development, sector expert who are working in more than 10 countries, around the world. Field Ready Turkey has been working in northwest Syria and in Turkey since 2016. Our mission is to work within and to empower local communities to create sustainable solutions through innovation and entrepreneurship. The nature of our project is always based on the concept of localization, which means adapting. What adapting? Adapting the product and services that we create to specific local markets. By local manufacturing, either at the workshop or at the innovation hub. So it's called research and development centers. Our approach to problem solving has 5 key stages. They are first assessment, where we identify the problem. Then we design and develop the solution. Then we share, distribute, and train people on our product and services. Then we make local manufacturing entities. Then the last, we lead and influence the sector that we work in. So here's some quick overview on our latest project that we have done already over the last 2 years. Our team has developed an innovative and cost-effective solution, which is called SQA bags, made from locally recovered and recycled materials, including deployed vehicle airbag, that can be raised heavily. This one, that can be raised heavy debris, and help save anyone trapped beneath a collapsed structure. Luckily, our design works well and meets international standards at a 90% reduction in cost. Yeah. The second one, our team also made important, contribution to the healthcare sector in Syria. And at the beginning of 2020, our team began fixing some medical instrument and devices at 2 maker spaces in northwest Syria. By March 2022, we repaired more than 230 critical items, including nebulizers, ECG, electrocardiography, and ventilators needed to treat patients suffering from COVID-19 symptoms. Our team members also developed and manufactured spare parts to repair infant warmers or incubators, suction devices, and CT machine, the computed tomography. In addition to developing a number of critical items, we have developed also full cooling chillers and air filter for the operating room or the operating theater. Also, we have trained groups of people to use the hydroponic agriculture equipment and to create, sustainable and reliable food sources. This technology is, of course, we have adopted this technology in the area which they are under the BSAGE. And the least but not last, we have worked with some ambitious, partners under a project called the Waste for Warmth, and I'm going to elaborate more in the next slide. So during the last year, Field Ready Turkey has been working to improve the life of people living in temporary shelters in northwest Syria. We have been working to find ways to use upcycled plastic to help keep housing and shelter warmer. Our partners in this effort include Engineers Without Borders, Norway, and the Polyfloss Factory. We believe that we have found some innovative, solution, and we have built a prototype at our research and development workshop in Gaziantep. And also we have tested our product in Turkey, and we're going to test it in Syria as well in the near future. So let me just talk about the three products that we have developed this year. The first one is called the insulating panel, which we design it and manufacture it in order to use it inside the RHU panel. It keeps the indoor temperature cooler in the summer, and it keeps the indoor temperature hotter in the winter. And the panel is made of PET and airfoil and woven plastic, and it can be attached internally, as you can see here. And of course, the last 3 weeks we have insulated a complete RHU tent, and we have taken some temperature reading, and you can see how much temperature difference we have got. In fact, we have got more temperature difference. Maybe our colleague in Engineering Without Borders can highlight. And also we have made the second product, which is called the floor tile. The floor tile aims to floor the ground and the soil of the tent, because the soil of the tent is not even, and should be floored with some rigid material like a floor tile, so everyone can use it, sit on it, maybe walk on it. And it's fully 100% made of injected plastic, waste plastic, and different plastic can be used here. I can show you in this small short clip how it works. So here this is the soil inside the RHU tent, and we will place this tile on the floor, and then we can attach them with some dowel and cabinet strip fastener, etc. Yeah. And the next product is called the insulating tile, which is used for the external insulation of the houses, which is made of concrete. So of course here we use the expanded polystyrene, and inside the polystyrene is made of a box, and inside the box is empty and it's stuffed with the floss, and we just attach it on the wall, and then we have like a coating material on it, and it works fine. And this is the final shape of the product. This is the wall tile, and this is the coating of the wall. Apart from the product development and manufacturing, we also have conducted some workshop and training. We have conducted a design thinking workshop in 2011, where we train the people how to solve problems, generate creative ideas, and build rapid prototype. And finally, this year we were more than happy to welcome Mr. Karl to train us on the the health, safety, and environment, where we assess risks pertaining the polyfloss machine, and we defined hazard and the mitigation strategies. So what next? Our next plan is to insulate 10 RHU houses in Syria with our newly generated panels, and also to deliver training in product development to the people and students who are studying at universities, and also the entrepreneurs. Thank you very much for your listening.
Thank you very much for that presentation. Now we will ask if you can stop sharing, and then we'll let Karl Ove share more specifically about what he did in Gaziantep regarding sort of a risk assessment of the polyfloss machine.
Yeah, thank you, Holly. And good afternoon to everybody. For those who haven't met me before, Karl Ove Ingebrigsten, Holly, we're quite close, so thank you with my family name. I'm a mechanical engineer. At the time being, I'm working part-time for Norconsult. Rest of the time, I'm trying to be retired as much as I can. And with my connection to Engineer Without Border, I have been the chair of the board for the last two and a half years, and do also work for that. And then I had the opportunity this spring to be assigned to a specific task for the waste for warmth project. So here is a few picture of what I met actually in Gaziantep. I met two very nice, clever, good guys working hard to actually put the product out in the field. And I'm not sure if I should mention when we played table tennis, but we had some very nice games down there. So it was a very nice and personally a very learning-full trip. I have been working more than 30 years with HSE challenges in different areas, and for me this was a very nice opportunity to actually use my skills and experience within this area. And we had an agreement before we started that there was some key objective. We have quite a long list of different tasks, but I have selected to put 3 key objectives for my task. The key objective actually to ensure that we have a machine that's safe to operate in any way. When we put the machine out in the field, it should be safe to operate. It shouldn't harm any people, environment, and so on. Also to mention that more than a year ago, it was performed another safety study of the machine, very focusing on the fumes from the heating of the plastic. So I didn't spend time on that hazard, but we just mentioned it. So the method, which I will spend a few minutes on the next slide, that was to perform a hazard and identification and a safe job analysis in the operation of that machine, so it's safe to use. It's also a part of that the way we are working, or the way we worked as a team down there that week, they can use the same way of working in any kind of machine to identify the hazard and make any kind of machine safe to use. And of course, we made a report. We made a documentation of what we have done, and we make some reference to best practice, mitigation, how to do that, and some necessary recommendation to reduce the risk of operating the machine. And we did also some connection to emergency protocol if anything should go wrong with the machine. So that was the key objective of my task. The way we worked is actually very much based on the international standard of performing risk assessment, and also we have a Norwegian standard explaining how to do risk assessment. But what we try to do in the risk assessment, it's actually to identify what can go wrong. How often, what's trigger. For this, it can be a mechanical hazard, it can be electrical hazard, it can be thermal hazard, you can get burned, it's noise, vibration, all kind of hazard that we are afraid can take place. And that can be due to wrong operation. It can be due to bad design, any reason. And then we try to tell the story of why something happened. We have something that we would not like to happen, and at the end that will have a consequence. Of course, the worst case could be actually to have fatalities, but we didn't identify any kind of event that can make, let's say, fatalities. But you never know. We can never be sure that that can't happen. So this is a typical bow tie way of thinking, and we identify the barriers that prevent an event to develop to some consequence that we would like to not to see. We also applied quite standard and generic risk metrics, where we have the severity of the consequence, which it's insignificant to catastrophic, and we have the likelihood, how often it can happen. That means if we have a catastrophic event that happen quite often, that's in the red area, which is unacceptable. But if we have insignificant consequence and we don't think it will happen at all, it will be the green. So we made some definition of what we actually, when we talk about frequent event, that's something that we expect to happen every day when you operate a machine, and so on, and every month, once a year, and incredible. That's when it's expected to happen once during life of the use of the machine. So that's how we define the likelihood. The consequences, we started with insignificant events that do not need any kind of first aid. And then we have more severe type of consequences with the need of local first aid, and then more advanced treatment, and then at the end catastrophic, which we define as a very severe injury that need hospitalization. And that's how we define. So the objective for the whole study down there was to identify what can go wrong and what's the risk, and how can we actually reduce the risk. So what we did, actually, we were working quite hard as a team down there. It was really great and needed to have the Field Ready team down there, because they know how to operate it, they know how it works, they know the problems, they have hands-on experience on how it was used. So we identify a list of 32 hazards that have a consequence, and causes and a consequence. We listed some of the existing preventing measures that's already in place, and we estimated the likelihood and the consequence. And for this example, where we have a spinning head, that means that it's rotating parts that's not covered, and it can be touched by people, or person's clothes can fastening and you can get stuck. Person can be injured. That means that it's an unacceptable risk. And then we propose some mitigation, as an example, to install a cover that it should prevent us to be, let's say, hit the rotating part. We could establish safety walls and so on. And that's reduced both the likelihood and the consequence. And you see here it's in the green part. And we added also some comments on how to handle actually this hazard we started with. So we have in the report, we have a list of about 32 of these hazards that we went through and listed and proposed quite detailed how to mitigate the risk. And for some of them, we also add some comments. And all these mitigation have been now handed over both to Field Ready, but also to the polyfloss team, who have updated the machine with new risk reduction measurements, so it should be more safe to operate than the machine that we looked at down there. So that was the let's say the key way we worked. So the result, of course, it was a report, and when we had the first walk through the machine, we identified 7 hazards that we couldn't accept, and some yellow hazard that it's partly acceptable, but if it's, let's say, easy to do something, let's reduce it even more. If it's not cost effective or any other reason, we just let it stay. So after we had some discussions, we ended up with non-hazard in the red zone. We added 3 hazards that we think that we just need to live with those, and then the rest was green. So that's what we ended up with as a result. If you have any question, please just open the microphone and put the question on the air. Just to show you some of the hazard that we have been working with. Just to explain, here we have the machine. We put plastic here. Here we have the plastic. It's heated and pushed into this area, which is rotating equipment and also a fan. And the polyfloss will be blown to this kind of a grid and will be fixed on the grid. The polyfloss, when it's flying in the air, it's quite hot, so you can actually burn yourself if you are getting hit by it. And if you hit some part of the machine, you can actually get burned. And so here's an example that we made some comment about how to increase the safety and use of this grid system, which you actually can, when it's full of floss on one side, you turn it 180 degrees and then you remove the floss from the back side and you can carry on with the production. And here we propose some cover to protect the screw even more. Here are some details. It's something that rotates and it's hot and it's not very well protected. So we discuss how we can actually protect it even more. This blower ring, it's airflow, which make quite a high noise. And we were discussing how the noise be reduced? Can we do something? We have to remember that this machine quite often can be used in quite warm and with high humidity area. So to wear personal protective equipment can be quite uncomfortable and hard. So we actually pushed to see will it be possible to reduce the noise from the machine, and can it be possible to protect some of the rotating equipment even better, so clothes and fingers shouldn't be stuck into the machine. And one way of we already have some safety walls here in the test lab, and those need also to be out in the field. And we have here the area where you put the plastic into it, and you can even be stuck here with the finger into the screw. Some more details. Quite a lot of the hazard we run into and what we discussed, it's all about rotating equipment, and where you can put your finger or you can have clothes that been stuck, and that's quite dangerous. We spend quite a lot of time and looked on some of the international standard, the machine directive as an example, to look into how to protect the operator for different type of hazards. So this is just an example that it's actually an open hole, and if you by an accident put the finger into it, that you will lose part of the finger. Some of the rotating was quite open, and it could be very easy to cover, to put some cover on it to ensure that it's safe and safe in use. And we have a very a nice operation panel, which you add some temperature on the different temperature zones. And what we also identify that some of the operational description, the user guide, need to be updated. So you know quite well what temperature you should use in the machine when you have different type of plastic. And we also question that, is it really needed to have this this panel as close to the machine as it's shown here, because it, due to the noise and due to the possible toxic fume from the melting of the plastic. And here we have an emergency stop button to stop the machine. And here we have example of the floss that been produced. And as I said, it's relatively hot, and you can get severe burns if you are hit by the flying floss. But that's why it's really key to make some kind of a marking on the floor. Here we are seeing from above and down to the floor that you have an area which is hazardous, that it should not be allowed to enter during production, and you have some safety walls on the side. So we ended up with a long list. It's actually the appendix to the report of the hazards that we need to handle and take care of. The way we worked during the week, that we spend some time at the office. Sometimes we were walking around the machine and looked how we can reduce the risk. And hopefully maybe Almutan and Zakaria can make a comment, but I think we managed to exchange some skills and how to perform this hazard, and to document it in a way that's if they need to do a similar work on a machine next time, people like me do not need to go to Gaziantep, even though it's really nice town to visit. But it's better than people. It's better than people do it locally than we bring people all the way from Norway. That's not needed. So that's a very, let's say, short story about what we did. I have one slide more, but I can open for any question on the work and the assignment. Any questions? Yes, go ahead.
Yeah. Thank you. Very interesting project and very nice presentation from both of you. But both of you touched upon the concept of lifetime. How was more or less estimated the lifetime? So any one of you describe a bit, in particularly because it also affects one of the likelihood categories was incredible, which was defined as a once in a lifetime. But then what's the lifetime considered in for the machine? Anybody, any of it?
I can make a comment. That's a typical challenge when you do risk assessment of and to define how long, many years, months, weeks, or whatever the machine should operate. But we solved it in a way that we discussed, have they experienced this hazard during the test of the machine because the machine had been in operation for, yeah, you have to correct me, Al Montana, for a couple, 2-3 years. So if they haven't had that event, we thought it will be quite, let's say, low probability. But we didn't do any, let's say, assessment of the machine, how long it will be operated. But on the other hand, it's also a question about how good is the maintenance of the machine, because that's actually are the key here. If you do not maintain the machine well, it will change the way it operates, and then it can be really hazardous. So that's the challenge by doing this kind of assessment, that we just have to assume that the machine will be well maintained. If it's not well maintained, our, let's say, assessment will not be correct. And we know that that's a challenge. It's not necessary that they will maintain it. That means that the machine can be very hazardous to operate if it's not well maintained. But we need just to do an assumption that, well, it will be maintained, and that's part of the, let's say, delivery. Any comment from the Field Ready team?
If you allow me, I can add something. Actually, this machine like not design machine for manufacturing. It's just like test the machine to do some test on it. So that's why we received this machine in Gaziantep from our partner in France, polyfloss factory, and we did some work on the machine to understand how it's stable, what we can develop, what's the weakness point of this machine, and we prepared, and we always meeting with them, and we provide them with some reports in case for production the new machine, just to take our notes and work on it.
Thank you.
Any other questions, comments?
I have several, if nobody else has questions.
Just go ahead.
Yeah, were the parallel events considered? That's one. And I have another one. You mentioned with the rotating parts, the fact of being injured by touching it. But was there any consideration given to flying objects if something went wrong and then produce flying objects? Yeah, I mean, both of them parallel events and flying objects from the machine.
Yeah. Flying object, it's mainly the flying floss that's the problem. But of course, you could have disruption of some of the steel part, which is fixed to the machine. And then again, they can be, let's say, flying objects. How we solve that is a little bit on this drawing, that we identify an area where people shouldn't stay during operation, and that will protect them for that. And then the next question you raise is actually parallel or simultaneously
events. Yeah, you're correct.
In some way that you can get burn and you can stick your finger at the same time.
For example.
Yeah. In some way, we handle those as independent events. That's the way we sort it out. Of course, we could have looked on what happened if you get burned and stuck your finger or your clothes at the same time. But I'm used to look on that, let's say, as separate event, because it's separate reason or causes of the different.
Yeah, my question was more because in my experience, catastrophes happen when several barriers are disappear, and then starting to occur things simultaneously. For example, that I got burned, and in the movement, in the reaction of getting burned, I put my hand near the rotating part and so on. That's when catastrophes or it's a major catastrophic consequences tend to happen.
I'm agree, and we in some way the way we sorted that we actually tried to put cover on any part that's above a certain temperature. So you remove that hazard in totally. And the same with the rotating, but except the rotating and the heat in the front, the only way to protect it is actually to ensure that people will not stay here. Because if you can't do anything, because here it's flying polyfloss with high temperature. And okay, you can build a totally enclosement, but I think that's it's all about training people.
Okay, thank you.
Okay.
Sorry, I've got a question, David Osborne here. I may have missed this because I was a bit late to the meeting, sorry about that, but the risk matrix that was used to define what was unacceptable versus, is that a standard? Is that a kind of a general risk matrix from industry, or?
Yes and no. Yes, it's quite standard that it's some have 3 by 3 and some have 5 by 5 or 7 by 5. There's different standards, and but let's say the standard way of showing it that you have it in this way with a red part that's not acceptable, and then something in between, and then something that's acceptable.
Yeah.
So the way it's we applied it, that's what we selected in this project. But you will find the same way in general industry, and how it's explained in like the international standard, how you should apply risk metrics. So yes, it's standard, but at the same time, it's tailor-made for this project.
I see. Okay, thank you.
I can add that EVB uses the same in risk assessment when it comes to security for sending people to the field. Same matrix. I have a question as well, Karl Ove. It's maybe not so specific to this HSE assignment, but generally speaking, from an HSE point of view, what would your considerations be comparing open source machinery to a polyfloss machine, for instance? If you understand the question.
Yeah, I will try, and then you can comment if I understood it or not. I'm not sure if the machine is the key concern. I will end up with this in my final slide, but it's quite dependent on how you train the people who is going to operate it. If the people who are going to operate it don't know how to operate it, do not have the correct training, do not have the correct skills, do not behave how we expect them they should behave, and then we go into culture and education and so on. So in some way, to make the machine safe, if it's let's say from the shelf very advanced or open sources, I think the machine can be done quite safe, but it's all about the people who operate it, how they behave. That's my concern. I'm not sure if I answered your question.
Yes, well, partly. Because when it comes to, if it's something you put together yourself, like building from open source drawings, then obviously there's a lot more inherent hazards or potential hazards in that. And considering that is quite often solutions that we have also proposed in other projects. So I don't know, more kind of a deliberation around the topic and EVB's potential responsibility when recommending open source solutions.
But in some way,
a big question.
My personal view that as long as you whatever way you make in the machine, if it's based on open sources and you put all kind of things together, or if it's a professional who design it and build it, both need to look into the safety of operation of the machine, whatever, and that's the key. If you do it, if you buy something from a professional vendor, or if you put something that's that's you just put together and you think it works. You should make an analysis like we did before you start to operate it, and that's the key. If you don't, then I will be more afraid of something homemade of open sources than professional.
Thank you. And thank you, Karl Ove and Almutana and Sakuya for your presentations. It's been really nice to listen to while I was speaking.
Thank you.
Are you finally? Are you going to? Do you have any recommendations at the end, Karl Ove?
We have a long list of recommendations which I will now start to go into, and we first of all I show this because this is training, and when you try to operate a machine that can hurt you, it's really key that you are well trained as an operator and also as a designer. And what we did here, we spent one day at the university at the Technopark. We ran a training session on how to perform a risk assessment, how to identify risk. Zakaria had a very hard time because he needed to translate my English into 2 other languages, but he managed it quite well. I tried to look on the students, but no one was sleeping. So, yeah, but that was that's quite a nice day we spent there to train people in how to actually do what we did during the week to identify and have a well-documented process that you know what can go wrong and what I should be afraid of. So the recommendation that I think the key recommendation from my viewpoint is actually back to that it's really key that we have operator of the machine who knows what's the hazards and knows what can go wrong and know how to operate it. That's the key. And then the next level of, let's say, recommendation is to put cover on every places where you can put your finger or you can put a piece of clothes or whatever that you can start cover it to make it safe. We know in the front of the machine that's not possible, and there we propose that you should maybe make something red on the floor, that you shouldn't stay on the red part during operation of the machine. You should have some safety walls to protect for flying polyfloss. So to ensure that you protect people in some way. So it's actually a very simple recommendation, but make protection. And not only for rotating, but also for the hot surfaces that need to be covered because it's quite hot surfaces. The machine we looked on have some electrical motors, and none of them had, let's say, protection of getting too hot or running out of, let's say, breaking down. So when you make the final machine, you should ensure that you have some electrical motor with inherent safety for not being overheated and overloaded. The blower, it's making incredible noise. We need to do something with that. Either design it in a way or see how we can solve that. One of the challenges that we didn't look into is the possible toxic fume from the melting of the plastic. The only way of, let's say, identify if that's a problem or not is actually to do on-site gas measurement. You need equipment to measure that gas concentration. And I have been talking to Holly and proposed some people that can actually do that kind of measurement. But that's the only way. So that's one of the yellow part here to, in some way, we don't believe that this is extremely hazardous fumes, but we need to document that that's okay. So that's one of the, let's say, yellow part. And then more on the, let's say, operational part, that as an example, it should be first aid equipment with really focusing on burns, hot surface close to the machine, so people can get first aid if you actually get burned. You should also update the operational manual to be a little bit more detailed. So if you know the plastic, you should know the temperature, you should use the machine to control. Also, the machine need to be installed, and at the moment it's quite heavy. And we need to think about how that machine can be handled without breaking the back of the people and so on when they install it. So that was some of the let's say recommendation that were given in the report. So back to this training, I can't recall how many students that participated, but we managed to bring some new skills into the techno part, and hopefully I managed to bring some new skills to the Field Ready team. I learned quite a lot personally on the challenges that you run into when you bring this kind of machine into the refugee park and so on, and we discussed that. And I will really say thank you to Zakaria and Almontana on all the discussion we had and all the learning point from everything from life in Syria and the challenges we ran into in Turkey and so on. So it was really a learningful trip for me. So this is the team on the right side that had the training, and we have Ahmad here is I'm correct, that's the manager of the local Field Ready team. Yeah, that's all from my side. I can stop sharing.